to make sure that you're putting these together correctly. So we're going to do a form of bomb calorimetry next Tuesday. We're going to use styrofoam cups to actually get to see heat transfer. It's really neat to see your data from the molarity titrations yesterday. It was a really fun lab to see. All the pink solutions and pretty good data, pretty precise data. So it was neat to see that as a class. We're going to see this next Tuesday when we get to actually calculate heat movement from the system to the surrounding to see how much heat is given off in certain reactions. So we'll get to apply this type of chemistry next Tuesday. Now, with this, one thing we can do as chemists is we can actually determine the heat from a system to the surrounding on certain compounds if we use this technique called bomb calorimetry. And technically, right here at the bottom, you'll see this. Technically, this is delta E, not delta H, but it's close enough that we approximate it as the enthalpy of the reaction. Now, I showed you this table here, and this is how we get this data. This data has been actually experimentally determined over the course of the years, hundreds of years of this type of work being done to tabulate this data. This here, the standard heat enthalpies of formation are standardized worldwide at 25 degrees centigrade at 1 atmosphere, okay? So some of the work was done in Great Britain, some of it was done in America, some of it was done in Japan. But what happens over time is we are able to standardize this, and I'll show you what this would actually look like. You can find databases, and the CRC in the general chemistry lab has this, and you can just scroll down through and see all the data that's been determined over the years. One of the things you need to or look at as we scroll down through this is every single category. I shouldn't say every single, but for the most part, they all start with 0. Why do you think that is? 0, 0, 0. 0, 0, 0, 0. It's a really important thing to make note of. It's because these are state functions. We can't know the internal energy of an aluminum atom. All right? So we start with, this is where Hess's law starts with. Every compound, or excuse me, every element in its elemental form is 0. So that's where you have to know your diatomic elements. Hydrogen is 0 if it's H2, not if it's H+. Nitrogen is 0 if it's N2. Oxygen is 0 if it's O2. Fluoride 0 F2. Cl2 Br2 I2. So remember, 7 diatomic. Everything else in its elemental form, aluminum metal as an element, is 0. Okay? So that's why on a table like this, you can use the data if we're actually talking about the enthalpy, these enthalpy values here. Notice I kept mentioning Gibbs free energy, and that's right here. That's what you're going to talk about next semester, okay, with Dr. Harris. So this is the enthalpy, which we're talking about the heat. This is the Gibbs free energy. Very different because that brings in the concept of entropy and enthalpy working together. Okay, and here you can see that over here with the enthalpy, or excuse me, entropy. So again, you can scroll down through this, and there's a lot of data on these types of websites, and also in the CRC. And you can just, all this has been experimentally determined, as has this and as has this. So a lot of tabulation through the years, and we actually look at it in the general chemistry course in a pretty nice, tight little package, right? This little tiny table, but just know this table is massive. Okay, so we're just going to cherry pick a few compounds out, show you how this works. But again, in the big picture, we know quite a bit of data coming out of something like this. Now, how do we actually use this, and how does this actually work pragmatically in the real world? Well, it's pretty cool, actually, how we use this. Hess's law says that we may not know how to get from A to B. We might not know how to get from A to B. But if I can add up enough steps between A and B, then I can approximate to a really high level of accuracy what A to D, excuse me, I keep saying A to B, A to D. So I can't get from A to D directly. Ish. I actually can if I use, again, calorimetry. But if I know the steps from A to B, B to C, and C to D, I can theoretically add all those up and get from A to D. And that's what Hess's law states. And that's what we're actually going to do. And this is the final part of chapter 5, Hess's law, working Hess's law, working some of these problems. So you can see that if magnesium to magnesium chloride is what I want to know, I can do magnesium to magnesium oxide to magnesium hydroxide then to magnesium chloride. So if I don't know the actual reaction, I can use other reactions along the pathway, and Hess's law gets us to where we want to go with the reaction from magnesium to magnesium chloride. Now, here's what I will say about these calculations. They are laborious in detail. You have got to keep your reactants and your products and the signs of the energy, whether it's endothermic or exothermic, consistent. This is where I see typically people get really confused with these. I'm going to work with, I'll show you how confusing they really are. And you have to just go in and make sure everything is consistent. And a lot of times I think students can go awry when they try to do it all on their calculator and don't write it down. These are the types that you really do want to write down and see how they flow. Because if you're on your calculator, 3 times a negative 442 minus 4 times a negative 300, all of a sudden it gets all messed up. Okay? So we're going to use Hess's law. Now, again, this is a state function, meaning that it doesn't matter how I get there, the path is going to be the same. That's what basically a state function states. So we can use these individual steps to do the overall reaction, which is what we're going to see. It's actually really pretty cool reaction. So let's see an example of this. If I go from methane, if I consume methane in oxygen, burn it, I'm going to burn methane gas. Methane gas burns. It's an exothermic reaction. It gives off heat. That's why we use it for Bunsen burners and other things like that. We can actually go from the reaction of carbon to carbon monoxide, carbon with water, and half an oxygen. I can calculate that. Then I can go in and calculate the difference of that, and I can get that one plus that one to give me that one. And that's basically what Hess's law does. I'm going to show you exactly how we do that by using these tables that I just showed you with the enthalpies of formation. Okay? So enthalpy of formation is this delta H sub F with a knot if it's standard at 25 degrees centigrade and 1 atmosphere, it will have a little knot up on it. That's why if you look back here on this, that right there tells me that it's 25 degrees centigrade, 1 atmosphere. Okay? And so you can see that right there. That's what that tells me. That's been standardized so that we all are talking about the same numbers, right? Law of identity. We've got to be talking about A in the same context, in the same way, in order to have rationality. The same thing happens in science. Okay? So here we go. Let's say I take a bigger molecule like propane, and I'm going to combust propane. And I'm going to see if I can calculate, using Hess's law, how much energy I should get out. I could do this experimentally. Yeah, I could use a calorimetry, and I could get that number out. I could also do it theoretically if I know the heats of formation. That's what we're going to do. So here's the way this works. Propane, okay, is going to decompose to graphite, 4 hydrogens, and 5 oxygens. Okay? So stay with me on this. What is the enthalpy? What is the enthalpy of formation for oxygen? You have it memorized, right there. What's the enthalpy of that? 0. You memorize that. And what's the enthalpy of hydrogen? 0. You memorize that. Okay. You memorize that because any element in its elemental form is 0. So that's the only part of the table you need to memorize. Okay. Makes it pretty easy. Any element is 0. So that tells me that what is the heat of formation, the enthalpy of formation for propane. Oh, well, then I go up to my trusty dusty table, and it, lo and behold, looks like propane up there is negative 3.45. But notice I had to make it positive 3.5 because it requires energy. Okay? It requires a match to light the propane. It has to have energy in order to get the system going. That's why it's uphill. Okay? Now, once I'm uphill, I know that I have negative 103.85 to initiate this one. Now I'm going to have 3 carbons plus the oxygens going to 3 carbon dioxides. Oh, well, I can go up here to carbon dioxide and find it right here. It's negative 393.5. Okay, that's negative. Again, you have to follow the sign, exothermic, so it's going to be negative. It's giving off heat. Then I can find the heat of formation for my 4 waters. Okay, 4 waters in the liquid form is going to be 4 times negative 2, whatever that is, if you can actually read it up there, 285.8. Okay, so if I add up 3 times the carbon dioxide, 4 times the water, that gives me negative 111 or 1181, negative 1143. Add those together to a negative. Remove 103 for the destruction of the propane, and notice I get out the heat of the reaction. Isn't that kind of cool? And that's using Hess's law. So this is enthalpy 1, enthalpy 2, enthalpy 3, add it all together. They give me the total combustion of propane. So let's break that down. Hess's law says this: delta H, the summation of the number of moles for products, minus the summation of the number of moles, the heats of formation of reactants. There you go. There's Hess's law in mathematical terms. So one big, giant subtraction, addition problem. That's all it is. All right, again, like I said, they do get a little bit crazy, so keep track of your signs, keep track of your stoichiometry, and they just take a little bit of work at getting through. Yeah.
So if you have 3, is the
3.
The coefficients increase?
3 carbon. Say it again.
If you have 3 reactants,
No, same thing. It's just your coefficients. Yeah. Again, reactants minus products. Okay. And you would just basically have 3 sets of equations, or 3 on one side and 2 on the other. Each molecule has an equation,
right,
unless it's an element, and then it's just 0. Okay?
So everything cancels because you're working in terms of that.
Yeah. Yep. Okay. So here are my 3 reactions. I'm going to go from propane to graphite. All right, that's endothermic. It requires energy to do that. I have graphite and water, or an oxygen, going to carbon dioxide. Notice the graphites are going to cancel. That's kind of cool. Okay. I have hydrogen and oxygen going to water. Oh, well, that's kind of cool because the hydrogens and the hydrogens are going to cancel. Graphite's going to cancel. Oxygen's going to cancel. Most of it's going to cancel, and I get the overall reaction. And you can see that up here. So here's what happens with these reactions. What I want to do is I want to look at this and go, okay, I know that graphite is actually one of the elemental forms of carbon, by the way. So it is 0. Well, let me go back to this table. This is actually kind of interesting just because I'm a carbon geek. There are several allotropes of carbon. So if you look at the allotropes of carbon, let me pull that website back up. Look at the allotropes of carbon, because we have Buckminster fullerene, we have a couple, we have diamond, we have graphite. If we go to carbon on this, there's a lot of carbon. So here you go. So graphite is what we consider elemental carbon. Okay, so that's why it's 0. Diamond actually has a little bit more energy in it because of its lattice. It has an sp3 carbon lattice, which has more energy stored within it, so it's 1.9 kilojoules. But then we get into the fullerene family, the C60 and the C70, which are those buckyballs, those soccer balls. And you can see they have an incredible amount of energy stored within them. So graphite itself is the elemental form of carbon that we use, and that's why when we go back to this problem that we were working through here together, we use graphite on it, okay? So, again, overall reaction, reactants minus products, and we should be able to get the overall reaction now, okay? So let's work the problem, just like on the Martian. Work the problem. You work enough problems, you get to come home. Okay, so with that, notice what I'm going to do. I'm going to take 3, okay, times the negative 3. Remember, it's reactants minus products. Okay, we good? Reactants minus products. And something just happened up here that I'm going to have to explain to you, because notice I use the negative 103 from propane, but it's on the product side, so it's going to become a positive sign. Does that make sense? Explain that again. When I told you this reaction up here was endothermic, some of you should have been thinking, how did he know that? That's what I would have been thinking. How did you know that initial reaction was endothermic? because the table says negative. Ah, it is a reactant, not a product. Remember, this is products minus reactants. So if you subtract a negative, you end up with a positive. Okay, so that's how I knew it was endothermic. It required energy, didn't give up energy. Okay, just whatever that's worth. If that helps anybody, great. Okay, there's my reaction. Here we go. These are my products. Here's my minus sign. Here are my reactants. Again, one big massive subtraction and multiplication, or addition and multiplication thing. Okay, so here is my propane. Here is my propane. Okay, reactants, propane. One propane molecule. I go up to my trusty dusty table and I see propane's over here somewhere, and there it is, negative 103.85 kilojoules. Okay, so I have one of those at negative 103.85. Are we tracking? All I do is grab that out of the table, and I have one of them because my stoichiometry says 1. Okay, I then want to find out my enthalpy of formation for oxygen. I go to my oh no, I memorized that one. What is it? 0. So that's why I have 5 times 0 here, just to keep it consistent, to show you that 5, 0 is coming from that 5, 0. Does that make sense? Okay, so those are all of my reactants. They're all ready to roll. Now I'm going to go over and do my products. So I go to my carbon dioxide gas, and it does matter because notice water as a vapor and water as a gas has a different enthalpy. All right, so in this case, I'm going to go to my carbon dioxide gas, make sure it's gas, and it's negative 393.5. I have 3 of those because my stoichiometry says 3. I'm going to add that, or remember, it's the sum of the stoichiometric ratios, okay, for the reactants minus the products, or products minus reactants. Now I'm going to go to my water, go to my trusty dusty table, water liquid right here, and I can see that it's 285.8. All right, again, it's negative, so I have 4 of those. So I'm going to have 3 times negative 393.5, 4 times negative 285.5, 1 times 103, and then I'm going to keep adding all these up. Okay, so I get a big number here, negative 111, 80.5, plus negative 1143.2, minus a negative 103.85 plus 0. So as I do this, this and this added together is 23.7 minus a negative 103, which means I add it. Again, that's why that was endothermic. And so you can see that overall, it becomes 2,219.9 kilojoules, and lo and behold, it's pretty cool. Okay? So that's using Hess's law and standard heat formation. Okay? I don't think they're tricky, but they do require thinking through how the reactions work and setting up those equations. Okay? And that's where we typically get lost. All right? Questions on that? This is worksheet time. Best way to learn these is just to grind through a few. Yes?
I'm still just a little confused
Yes.
as to how you can figure delta degrees of
Yes. Here, go back here. This is the key. Okay? It is products minus reactants. So if my reactant has a negative enthalpy of formation, I'm going to subtract a negative, therefore it's adding that much, which tells me that was an endothermic process. Does that make sense?
Yeah.
Because it required that. And that's why the graph here, the graph is I think the graph is helpful. It required this much. How much did it require? Well, it requires what the formation of propane is, it's just the opposite sign. Okay? Okay, I know. You just have to kind of think that through. It's the negative, I'm subtracting a negative, therefore I'm adding, therefore that was endothermic. Because I get positive energy out, which means I had to put that much energy to break it apart before I could form the reactants, or the products. Okay?
All right.
Okay? Yes? Sasha?
So do you basically just figure it out by knowing what the end product Yes, yes. You don't have to know whether it's endothermic or exothermic. That's, to me, it's neither here nor there. I just wanted to show you that that's what's going on. Because again, if these are my, again, these are my reactants, okay? I really have to break them apart in order to put them back together. It just costs energy to break them apart. That's really what we're saying. Okay? So we're gonna break the whole thing together apart, and then we're gonna rearrange them, and we can calculate how we're rearranging them on those other equations. Okay? So again, I think the more we just work these problems, you'll start to see how this kind of plays out. Okay. Any other questions? Those are great questions. Good? Okay. All right, that's all I've got on that. So let's, let me grab, they're still on the printer, hang on. I'll be right back.